issue is on quantum computing and artificial intelligence. Let us begin with the proceedings of Edu with a Sanskrit sloka. Saraswati Namaskar. Varade Kamarupini. Vidyaramba Karishyami. With the divine blessings of Goddess Saraswati, the embodiment of knowledge and wisdom, let us move forward in the pursuit of learning and discovery in 2026. Organized by Department of Mathematics and KFTS. Now I request Dr. Shilpi Ma'am, Assistant Professor, Department of Mathematics, to kindly present the profile of today's resource person, Dr. Venkata Sundarananda Pucham. Please welcome, ma'am.
Thank you, ma'am. Good morning,
everyone.
I am
Dr. Shilpi, Assistant Professor
from the Department of Mathematics,
KLES University. Today I am here to introduce the profile of Dr. P.V. Sundaranand sir.
Dr.
Dr. P.V. Sundaranand sir is a professor and head of the Department of Mathematics at Rayalaseema University, Kurnool, India. He has extensive experience in teaching, research, and academic leadership in the fields of mathematics. His research interests span several areas of pure and applied mathematics, and he has made significant contributions to the discipline, scholarly publications, conference presentations, and by mentoring postgraduate and doctoral students. As the head of department, Dr. P.V. Sundaranand actively promotes research initiatives, collaborations, encourages academic collaborations, and supports capacity building among young researchers. He is deeply committed to advancing mathematical sciences and strengthening higher education through innovative teaching and active participation in national and international conferences. It is indeed an honor to introduce such a distinguished admission. Thank you, sir. Thank you.
Thank you, ma'am. It is my privilege to invite Dr. Venkata Sundarananda Pucha, Professor and Head of the Department of Mathematics, Rayalaseema University, who is joining us online to deliver a keynote lecture. Sir, we are delighted to have you with us today, sir. I request you to kindly share your thoughts and knowledge with us, sir. Please, sir. Please hand over the station, sir.
Yeah, thank you, ma'am. Thank you, Dr. Smriti, for your generous words. Thanks a lot, but I don't deserve all those things. But it is your kindness. Thank you. And so I take this opportunity to thank KL University in general, the Department of Mathematics, and all the organizers in particular. My special thanks to Dr. Satish Garu, who contacted me and gave me the opportunity to share this morning with you all. So sorry for the inconvenience. I had the issue with the audio. I hope now it's
no issues, sir. No issues.
Yeah.
Please go through.
Yeah.
Thank you, sir.
So actually, the title of the conference is Quantum Computing and Artificial Intelligence. When we really look at nowadays, these two are the buzzwords. So basically, I am from maths department. What I thought is, if I want to talk on it, I would like to start from optimization, which is vital in artificial intelligence. And of course, quantum computing to some extent it is okay, but as far as the computing is concerned, optimization is not that needed because the computation power is going to really increase exponentially there. Okay. Now, today, I would like to discuss optimization, nucleus of artificial intelligence and machine learning. Okay. So let me start with the saying of Pascal. If I had more time, I would have written you a shorter letter. Okay, that's the importance of optimization. Okay. So let me start with a simple problem. A farmer has 2400 feet of fencing and wants to fence off a rectangular field that borders a straight river. He needs no fence along the river. What are the dimensions of the field that has the largest area? Idea is, what we really want is, you know, you would like to optimize the area. Okay. So if I take these dimensions 100, 100, 2200, area is 220 square feet, 700, 700, 1000, it is 700,000. And if I take some other thing, 1000, 1400, it is 400,000 square feet. So it is like a constraint optimization. So I don't require a fence along the river. So the simple problem is A is equal to xy. Constraint is 2x plus y equal to 2400. And A is 720,000, x is 600, 1200. So I would like to maximize A subject to the constraint 2x plus y is equal to 2400. Okay. It's a simple optimization problem. You can call it as a constraint optimization. So in math, all of us really do discuss about optimization of functions of more than one variable. Suppose if I am having a function of n variables, f of x1, x2, xn, I would like to optimize it. Unconstrained optimization, I would like to just minimize this function. There are no constraints at all. In the constraints, I am going to have if x is greater than 0 is one constraint, or x is lying between minus 2y and y is greater than or equal to 1, another constraint. Like that we can think of. So whenever we do that, we know that whenever we are having a function y, if you want to either maximize it or minimize it, and we always find its derivative. Okay. So, and if we can find the second derivative, and second derivative is less than or equal to 0, maximum equal to 0 is an inflection, point of inflection. F double dash x greater than or equal to 0, it's going to be minimum. So second derivative type of the stationary point, how it looks like. So now the problem in artificial intelligence is local versus global. So we can always find a minimum, but in a particular interval. Whenever that interval really expands, what's going to happen? And suppose I'm having a global minimum and a local minimum. So you can see that this is a local minimum, this is a global minimum. So how to go from local to global? So this is the local minimum, but you need to find this. Okay. The entire artificial intelligence or machine learning is going to surf around this, going from local to global. Most of the times we'll be surfing here, verifying and validating it here in this particular interval, and able to understand that it is a minimum. But unfortunately, if you go beyond, this is the global minimum. Okay. So who contributed to optimization? Newton, development of differential calculus, Lagrange, calculus of variations, minimization of functionals, and optimization of constraint problems. And Cauchy, it is solution by direct substitution, steepest descent method for unconstrained optimization. And Euler, through calculus of variations, minimization of functionals. Leibniz, a differential calculus for optimization. And Danzy, who really worked on simplex method and linear programming, and Richard Bellman, and optimality in dynamic programming problems, and William Kuhn. It is a pioneer in the development of linear and nonlinear programming, popularly known as Kuhn-Tucker methods. Next is William Tucker, and he established necessary and sufficient conditions for the optimal solution of programming problems, especially nonlinear programming, game theory, and he is the guru of none other than John Nash and von Neumann game theory. And these are the people who contributed to optimization in a big way. So whenever we really look at optimization, we keep hearing, listening about the following no, algorithms. So optimization algorithms, if you take them, deterministic, LPP, nonlinear programming, mixed integer linear programming, mixed integer nonlinear programming, and if you go to Monte Carlo algorithms, hill climbing, tabu search, simulated annealing, random optimization, and if you go to evolutionary computation, evolutionary algorithm like genetic programming, evolutionary programming, strategy, evolutionary strategies, differential evolution, genetic algorithms, and nature-inspired ones. What are the nature-inspired ones? One is swarm intelligence, and another is bio-inspired. From swarm, we are having particle swarm optimization, ant colony optimization, and firelay optimization, bat algorithms, and in a bio-inspired fatty field algorithm, artificial immune networks. There are some other important meta-heuristic ones, a mind blasting algorithm, water cycle algorithm, harmony search, so on and so forth. So many combinations of these are also being used. You know, we know that human beings can think. Now, question is, can computers think or a machine think? Okay, thinking capacity of computers is identically equal to human being? No. Approximately equal to human being? No, not equal to human beings. It is a big question. Okay. If you want to talk about artificial intelligence, computers making decisions in the real world problems, and you formulate the problem, you solve it, you apply it again, you reformulate it. It's works on the feedback mechanism. And artificial intelligence is going to have expert systems and speech, case-based reasoning, neural networks, NLPs, soft computing, intelligent agents. Okay. And all those can be used for learning, reasoning, problem solving, perception, language understanding, so on and so forth. Okay. It's a pictorial view of AI. So let me start with speech recognition. How speech recognition is going to work. Okay. We always give voice input. I'm talking something. There are sound waves. They will be converted into some either analog waves or digital waves, something else. Thereby, receptor is going to receive it. Voice input to analog, and this is analog to digital. Then you can have an acoustic model. Then you can have a language model. We are going to have a speech engine, and there will be a display. Again, you are going to have feedback. It will go to the speech engine again. That's how speech recognition is going to work. So, whereas we human beings are able to hear something, because we will be talking, it will be coming out of our mouth, and it is going to reach the ears. And in the ear, there is some science. I don't want to go into that. Articulation produces sound waves. The ear conveys to the brain for processing. Okay, that's most important. So, how computers are going to work? We are going to have acoustic, which are in the waveform, and they are going to get it to an acoustic signal. You are going to digitize it, and you'll be doing analysis of the speech signal and linguistic interpretation. Thereby, you can really recognize the speech. What is the process? Digitization, signal processing, phonetics, phonology, lexicology, and syntax. All these are known to us. Converting analog to digital, separating speech from background noise, variability in the human speech, recognizing individual sound distinctions, and lexicology is a part of linguistics which studies words, their nature, meaning, element of the words, relation between the words, groups, and whole lexicon. Okay. So here, so previously we were having All India Radio and switch on to with Bharti or any station. And then it is going to have a speaker recognition. Who is speaking and what is he saying? What is he talking about? Then you can have a parsing and arbitration. Okay. Then you can have, whenever you switch S1, S2, SKS, and you can have different channels, inferring and execution. Okay. So you can understand that in the entire speech recognition, so digitization and what you are doing is you are doing some sort of an optimization where so optimization comes in conversion and reconstruction. That's an important feature of it. Then let us consider expert systems. We model human knowledge as a set of rules that are collectively called knowledge base. There can be any number of rules, 100 or 200 or 10,000 and 1 lakh, depending on the complexity of the problem. And there is an inference engine which searches through the rules and fires those rules that are triggered by facts gathered and entered by the user. And they are used for classification in which relatively alternative outcomes, in which these plausible outcomes are all known in advance in a structured decision-making situations. We are all non-expert users. There is a query, there is a user interface, inference engine, knowledge base. We are going to have the expert. And expert is going to give back inference engine, then user, he will be getting some advice. He is giving a query, he is getting some advice. But most important part of it, knowledge from an expert. Okay. So user interface, inference engine, knowledge base. Idea is we need to refine the entire repository. So it is very difficult, but refining is most important. So there is an explanation facility, inference engine, knowledge base, and this knowledge base, you keep on refining it or updating it. There is a user interface, experts will be there, and user will be there. This is how it looks like. And if you go a bit deep, there is a domain expert, a knowledge engineer, a knowledge user. Okay. So you need to determine requirements, identifying experts, construct expert system components, implementing results, maintaining and reviewing systems. And the area of knowledge addressed by the expert system. Okay. Can explain the reasoning or suggested decisions, display intelligent behavior, draw conclusions from complex relationships, provide portable knowledge. It is nothing but a collection of software packages and tools used to develop expert systems. You can really classify expert systems, rule-based, frame-based, neural expert systems, fuzzy expert systems, neuro-fuzzy expert systems. What are the applications? Information management, hospitals and medical facilities, desk management, employee performance, loan analysis, virus detection, repair and maintenance projects, waterhouse optimization. Okay. What are the limitations of expert systems? They are not widely used or tested, limited to relatively narrow problems, cannot readily deal with mixed knowledge, possibility of error is very much there, cannot refine and own knowledge base, difficult to maintain, may have high development costs, and ethical and legal issues may be there. Okay. And here also, you are having one problem which is called optimization. So optimization is you need to maximize the repository. Okay. And you need to optimize, that rules. And whenever you are having domain, you really have to make it as big as possible. But you need to employ experts who are having, experience in various fields. Okay, these are the limitations. Then is NLP, natural language processing. Okay, so it is nothing but computer communication, and human beings can communicate. But if you want two systems to communicate each other, what we really require is they should communicate and they should understand. One machine should understand another machine. Okay, so it is some sort of an interaction between the computers. So if I am taking some spoken or typed sentences, working out what it means. Some take any English sentence because we can understand the meaning of it. We know the language, we know the grammar, we know the usage. We are able to have cognition. Because of understanding, we are able to understand the meaning of a sentence. Okay. The meaning of a sentence is not ambiguous. It is not going to have two meanings. It is going to have only one meaning at all. Okay. So NLP is amalgamation of various fields: linguistics, psychology, philosophy, computer science, math, statistics, so on and so forth. So mapping the given input in natural language into useful representations. Okay. What are the difficulties? Lexical ambiguity, syntax level ambiguity, referential ambiguity. Okay. So ambiguity means you can have more than one meaning which you can draw. Word level, board as a noun or verb. If board is there, is it noun or verb? We can understand. Okay. Syntax level. Suppose he lifted the beetle with a red cap. Did he use cap to lift the beetle or he lifted a beetle that had a red cap? And a referential ambiguity. And, she said, I'm tired. Exactly who is tired? Rima went to Gauri. She said, I'm tired. And one input can mean different meanings. So many inputs can mean the same thing. So natural language generation. It is going to have test planning, sentence planning, test realization, retrieving the relevant content from the knowledge base, and choosing required words, forming meaningful phrases, and setting a tone of the sentence. And realization is mapping sentence plan into sentence structure. So we do lexical analysis, syntactic analysis, semantic analysis, discourse integration, pragmatic analysis. Okay. In this particular process, one of the important thing is CFG, context-free grammar. And here we are going to have a parser. So you are going to divide or classify each word into articles, nouns, noun phrases, verbs, verb phrases, adjectives, so on and so forth. If you are given a sentence, how to do that? Suppose I am having the bird pecks the grain. What is the and what is bird? Pecks. Again, what is the? Okay. And what are grains? Okay. So if you really want to understand the meaning of this particular sentence, you need to identify each word. Is it a verb or a noun or a pronoun or an adjective? Okay. So in this process, what we do is a top-down parser. And here, you see, so you are able to classify it. Okay. It is quite simple to implement, but it is inefficient, slow, as a search process has to be repeated if an error really occur. Okay. And what are the uses of NLP? Syntactic parsing to identify phrases, full syntactic structure comparison. Semantic, building an understanding of a document content. Discourse, exploiting document structure. So, simple phrase identification, high frequency terms could be good candidates. Terms co-occurring more often than chunks within small number of words, surrounding simple terms, not surrounding punctuation. What are the problems associated with them? Close words that aren't phrases, distinct words that are phrases. Okay. And whenever I'm having parsing, automatic analysis of syntactic test. Automatic is adjective, analysis is noun, of is preposition, scientific is adjective, text is again noun. Okay. Disambiguation. Given a word appearing in a certain context, disambiguators will tell you what sense it is. What are the errors? These are the errors. Analysis may be understood as, index document collections by senses rather than words. Ask the users what senses the query words are retrieve on senses. Okay. And what is the optimization there in NLP's optimization of NLP's components for robustness and scalability, graph models and optimization in natural language processing. These are the optimizations that are being used. Okay. And soft computing. Whenever we talk about soft computing, we should, mention or remember Jade is the father of logic. And soft computing is a coalition of methodologies which collectively constitute a system with wide-ranging capabilities for the conception, design, and operation of intelligent systems. Okay. And fuzzy logic, neural network, artificial immune networks, reinforcement learning, probabilistic learning, machine learning, evolutionary algorithm based on the origin of these species, swarm intelligence. All things can be studied under soft computing components. So, evolutionary computation, you can think about first generation, second generation, third generation. Okay. Evolutionary programming, genetic algorithms, and genetic evolution data structures, and so on and so forth. This already we have seen. So these are the various algorithms that are used. Okay. So because we are doing math now, and let me. There is a goal-based conjecture. Every even integer greater than 2 can be expressed as the sum of two primes. 3, 3 to 5, so on, is the smallest number that has no Goldbach's partition with a prime below 9781. So there is a unique prime factorization theorem. Every integer greater than 1 either is prime itself or is the product of prime numbers, and that this product is unique up to the order of the product. Sorry, up to the order of the factors. Okay. So this is how a discovery looks like. How can we teach things to computer? It is John McCarthy. In order for a program to be capable of learning something, it must first be capable of being told it. Okay. So if you are efficient in telling, it will become efficient in understanding. So now we are talking about artificial intelligence. It is a brain versus computer. There are 10 billion neurons, 60 trillion synapses, distributed processing, nonlinear processing, parallel processing, random search, what not. Whatever there is in the world is there in your brain. And all the brain is faster than a neuron, and central processing, arithmetic operation, their linearity, sequential processing. This your so-called computer is going to have. Brain is much more efficient, much more powerful. What are artificial neural networks? The models of the brain and nervous system. They are highly parallel. Uh, they they work on a simple principle, and they can even model the complex behaviors. And they are having many applications. Um, the structure of a ANN is you are going to give inputs, you can have weights, and you can have output, and of course you do have a bias. Okay, this is a simple architecture of any artificial neural network. And if you, it is learning. Neural network is all about learning, feed forward and back propagation, following data from input layer to reach the output layer after getting processed in the hidden layer is called feed forward neural network. Back propagation. It is going to calculate the error at output layer and propagate it back to adjust the weights and bias of minimize the error. So what is the first step? Initialize the weights and bias for each neuron and feed forward the information of input to hidden layers and then to output layer. Assess the error output of the network on the known output. Propagate the error backward to adjust the weights. Adjust the weights using gradients of change to reduce the errors. Okay. All of us, many of us do use numerical methods or something. We are quite used to iterations. But in neural networks, we use epoch. What is epoch? An epoch describes the number of times the algorithm sees the entire data set. So each time the algorithm has seen all samples in the data set, an epoch has been completed. Whereas iteration, it describes the number of times a batch of data passed through the algorithm. In the case of neural network, it means the forward pass and backward pass. So every time you pass a batch of data through the neural network, you completed an iteration. Suppose you have a data set of 10 examples, or you can call them as sample. You have a batch size of 2, and you have specified you want the algorithm to run for 3 epochs. So in each epoch, you have 5 batches. So 10 over 2 is 5. Each batch gets passed through the algorithm. Therefore, you have 5 iterations per epoch. Since you have specified 3 epochs, you have a total of 15 iterations for the training. Okay, 3 into 5 is 15. It's for the training. That's how distinguish iteration from epoch. What is the optimization of back propagation? There we have gradient descent, conjugate gradient descent back propagation with the momentum, the Pollock-Rayberry conjugate gradient descent. And you can have a Cauchy-Newton BP, Broyden, Fletcher, Goldfarb, and Shannon, BFGS, very popular, Newton's method. They are the optimization issues. Suppose there are neurons, 86 billion nerve cells connected to other 1,000 cells by axons. Stimuli from external environment or inputs from sensory organs are accepted by dendrites. These inputs create electric impulses which quickly travel through the neural network. A neuron can then send the message to other neuron to handle the issue or does not send it forward. So nodes imitate biological neurons of the human being. Neurons are connected by links and they interact with each other. They are neurons. The nodes can take input data and perform simple operations on the data. Results of these operations is passed to the other neurons. The output at each node is called its activation or node value. Each link is associated with a weight, ANNs are capable of learning, which takes place in the alternating weight values. You keep updating weights. How artificial neurons are going to work? Neurons work by processing information. They receive and provide information in the form of spikes. You are having inputs x1, x2, xn, weights w1, w2, wn. Here you are having it's a McCall-Pitts model. Here you are having z, wi, xi, y is equal to h of z. First of all, you are going to calculate wi, xi. Okay. And there is another function h of z, and that is your output. Okay. In the feed-forward ANN, unidirectional, no feedback loops, fixed inputs and outputs. There is a pattern generation, recognition. It's used for classification. They are feed-forward. Okay. Only in this direction they are going. Feedback. Here you can see it is going there, and from there it is coming back. It is a feedback ANN. And fully recurrent network, from here, everywhere you are having both way communication. And there is a Jordan network, inputs, hidden layers, and outputs. Closed loop network in which the output will go to the input again as feedback. Everywhere it is coming back. If the network generates a good or desired output, there is no need to attach the weights. If the network generates a poor or undesired output or an error, then the system alters the weights in order to improve the subsequent results. And machine learning in artificial neural networks. And we are having the following learnings. Supervised learning, unsupervised learning, reinforcement learning, backpropagation algorithm. Okay. Here, in the biological case, dendrite, cell body, axon. And that's how, but in the artificial neural network, inputs are there, synaptic weights will be there, summing junction will be there, activation function. Thereby you can have YK. Of course, you are having a threshold. Okay. This is a general, all these are artificial neural networks. They are inspired by human beings. Okay. What is the basic structure of ANN neurons? Layers. They are nothing but nodes. The fundamental units of neural network similar to the biological neurons. Layers, input layer, first layer where the data enters the network, hidden layers or intermediate layers between the input and output that transform inputs into something the output layer can use, output layer. The final layer that produces the predicted results are classification. You are having an input layer. All these are hidden layers, output layer. There will be a transformation. Okay. And they are coming here. That's how they are changing. You can understand that there is no feedback. They are not coming back. Okay. They go only forward. Here is the input. It will go to output. Of course, before reaching the final output, you are having hidden layers. Something is done. You can think them like a black box. So if you want to pitch it mathematically, so y is equal to f of x, y. We know linear is desired. Linear is easy to handle. But nature is non-linear. Nature is random. So if you want to simulate or if you want to model, you need the help of either nonlinear functions or random functions. So here we need nonlinear functions. Okay. Most of the time, science is all about either creating nonlinearity for simulation or solving nonlinearity and creating randomness or handling randomness. Okay. So nonlinear generalization. If I take y is equal to f of x comma w, and it is a neuron output, x is the input, w is the weight. So if I take y is equal to 1 by 1 plus e to the power of minus w transpose into x minus a, it is nothing but sigmoidal neuron. It is a Gaussian neuron. You know that all of us know probability density function of a normal distribution. And in particular, standard normal distribution is 1 by root 2 pi e to the power of minus of x minus mu whole square by 2 sigma square. Okay. And sorry, 1 by root 2 pi to the power of minus x square by 2. If you want to use a normal distribution with mean, mu, and variance sigma, 1 by root 2 pi to the power of minus half x minus mu whole square by 2 sigma square. Here A is our standard deviation, W is the mean. It's a Gauss neuron. And multi-layer perceptron network. Input layer, first hidden layer, second hidden, third. You can use as many hidden layers as possible. Okay. And it is for adaptivity, generalization ability, fault tolerance, and inspired from the biology. It is a multi-layer perceptron network. So single layer, multi-layer, radial basis, whole-field network, Boltzmann machine, self-organization map, and modular networks. Okay. It's a single layer perceptron architecture. We consider the architecture. Look at this. Only single layer. Inputs are there. Okay. So perceptron, it is a neuron model, uses a nonlinear model of the neuron. X1, X2, XM, W1, W2, WM. They are the weights. And here you are adding a bias. Now you are able to make V depending upon input, weights, and bias. And you are taking a function of V, you are calling it as Y. So I can take this phi of V, which is naturally your output. It's a sine function. So phi of V is equal to plus 1 if V is greater than or equal to 0, is minus 1 if it is less than 0. What are the applications? It is used for classification. Classify correctly a set of examples into one of the two classes. Feature extraction also. If the output of the perceptron is 1, then the input is assigned to class 1. Minus 1, it is assigned to class 2. So whenever we look at classification, suppose I am having a equation below. It describes it's a hyperplane. In the input space, the hyperplane is used to separate two classes, C1 and C2. So visualize that all are mixed. You are able to draw a line so that on the above they are all green, below they are all black. So it is greater than 0 and it is less than 0, equal to 0 is the line. It is a hyperplane. Sorry, hyperplane, two-dimensional. Multi-layer perceptron is going to be like this. There is a whole-field network, and here you are going to have 1, 2, 3 nodes and corresponding weights and biases. Okay. Suppose if I take a 3-layer network, input layer, hidden layer 1, hidden layer 2, and output. And there is no connection within a layer, no direct connection between input and output layers, fully connected between layers, often more than 3 layers. Number of output units need not be equal to number of input units. Number of hidden units per layer can be more or less than the input or output units. Each unit is a perceptron. So mathematically speaking, yi is equal to f of sigma wij xj plus bi. Of course, j running from 1 to m. And you can have a bias. Okay. And sometimes bias can be taken as extra weight. And if you look at back propagation or forward pass change, in the forward pass change, computers functional signal feed forward propagation of input pattern signals through network. Okay, here you see inputs, you are going them. Okay, all are going up. Okay, all are going up. Backward pass phase, computer's error signal propagates the error backwards through the network starting at output units and they need to come back. This is how forward, this is how back. Conceptually, forward activity and backward is error. Okay. What are the features of artificial neural networks? Records need to be represented as a set of tuples, attribute as well as value. Output value can be represented as a discrete value, a real value, or a vector of values. It is tolerant to noise in the input, time factor. It takes long time for training. Once trained, an ANN produces output values very fast. It is hard for human beings to interpret the process of prediction by ANN. So let us look at the genetic algorithms. They are proposed by John Henry Holland. It's a class of computerized search and optimization algorithm adopted from the process of natural genetics, natural selection and evolution. Okay. So before that, we started with speech recognition. Then we have seen escort systems. Then we have seen natural language processing. Then we have seen, to some extent, artificial neural networks. You can understand that everywhere optimization is playing a vital role. Now, let us have a pinch of the algorithms. So, it is natural selection and evolution. Genetic algorithm employs 3 different operators: selection, crossover, and mutation. Okay, mutation is very dangerous in the human beings, but mutation is very advantageous in the algorithms. Okay. In the first stage of selection, better chromosomes are selected with the help of selection operators. Crossover operator typically combines 2 different parents to produce new chromosome. They are nothing but solutions in our applications. In order to inject diversity into the solution and avoiding it to be trapped inside a local maxima or minima, the mutation operator is used. If you really CPSO, chaotic particle swarm optimization, it is one of the important types of swarm intelligence-based algorithms and proposed by Kennedy Eberhardt and she. This algorithm mimics the swarm of birds flying behavior and utilizes its ability to find a solution. Each particle in PSO denotes one bird, and each particle is assigned an initial location and a velocity. And there is a best particle we need to find according to the best particle as well as best location. Best particle, popularly known as P, best location as Z. The particles constantly update its velocity and location. In the basic PSO, the optimization approach employs the global best. okay, of the particle as a neighborhood topology. Each particle learns from previous best PI and global PG. You need to update them on a regular basis. And the chaotic PSO employs chaotic perturbations on best G to update the particle position. The chaotic perturbation helps in avoiding premature convergence and enables the algorithm to find global optimization solution. The updation of each particle is also influenced by its own best position, its previous velocity and global best position among the particles. Another is the differential evaluation. Kenneth B. Price, uh, he attempts to solve the Chebyshev polynomial fitting problem that had been posed to him by Rainer Storm. And differential evaluation is one of the evaluation algorithms that is used for global optimization over a continuous search space proposed by Storm and Price. Three operators, namely mutation, crossover, selection, defines the operation of differential evaluation. These operators have functions that are not exactly same with the same names in genetic algorithms. In the differential evolution, you can see population evolves through repeated cycles of these three main operations. The process can be summarized as mutation of three randomly selected vectors, creating a final vector by crossover of mutant vectors and targeted vectors. And unlike the genetic algorithms where parents are selected based on the fitness, every solution in DE takes turn to be a target vector. Thus, all the vectors play a role as one of the parents with certainty. This process ensures diversity and reduces the chances of good solution being eliminated. Next is Hope-field networks. O-field is composed of binary threshold units with recurrent connections between and their nonlinear units are generally very hard to analyze. They can behave in many different ways. And they settle to a stable state. Sometimes they oscillate, follow chaotic trajectories that cannot be predicted far into the future. All the nodes in the hopeful network are both inputs as well as outputs, and they are fully interconnected. Every node can be visualized as input as well as output. Everywhere you are going to have a feedback. But Hopefield realizes that if the connections are symmetric, there is a global energy function. Each configuration of the network has an energy. The binary threshold decision rule causes the network to settle to an energy minimum. So, we understood that there is optimization everywhere in the machine learning. Okay. There is an important feature called perceptron and gradient descent. Practically, if you take artificial neural network, I am going to have output of the input x1, x2, xn, maybe 1 whenever w0 x plus w1 x1 so on is greater than 0 minus 1 otherwise. Okay, you can have activation function, threshold function. Okay. So we know about least mean squares error. Okay. Whenever we are having a target or whenever we are having some estimate, you would like to compare it. So expectation of W bar is given by that quantity. D is the set of training examples. Okay. So output values O is the real value. It is not binary. Delta rule, learning rule for an unthreshold perceptron. It is gradient descent rule, also known as Windroff half rule. Okay, Windroff. So gradient is what? Nabla E of W bar is dou by dou W naught E, dou by dou W1, dou by dou Wn. Okay. What is the training rule? Whenever delta W bar is minus theta into nabla EW, that is delta Wi is equal to minus theta uh, dou by dou W of E. So in this case, what dou E by dou W is I will be getting this. What I am doing is I am finding the partial derivative with respect to each variable. So what are the limitations of gradient descent? Converging to a local minima can sometimes be quite slow. And many thousands of gradient descent steps. If there are multiple local minima in the error surface, then there is no guarantee that the procedure will find a global minimum. In the case of large number of hidden layers, this gradient descent fails to update the weights at the lower level, which is vanishing gradients. Solution is RBM. Okay. What is the problem of vanishing gradients? What happens to the magnitude of the gradients as we back propagate through many layers? So, whenever complexity problem is there, and if you need to improve the accuracy, you need to use many layers. But simply increasing the layers will not solve the problems. And it is going to pose a bigger problem. Okay, if the weights are small, the gradients shrinks exponentially. If the weights are big, gradients grow exponentially. Both are issues. Okay, feed-forward neural networks are backward. Even with good initial weights, it is very hard to detect that the current target outputs depends on an input from many times steps ago. So RNNs have difficulty dealing with long-range dependencies. In the case of large number of hidden layers, gradient descent fails to update the weights at the lower layers. So why the backpropagate gradient blows up? If we start at a trajectory within an attractor, small changes in where we start make no difference to where we end up, you can see. But if we start almost exactly on the boundary, tiny changes can make a huge difference. Okay, this is all theoretical stuff. Practically, whenever you do these artificial neural networks, suppose if I am using a logistic regression, I am taking y is equal to w dash x plus b. It is not used because given x, we want output to be the probability of y equal to 1. So our output must be between 0 and 1 so that we use a nonlinear function. It's a linear function. Don't be confused that neural networks are used only for classification problems, which is wrong. Neural nets are used for regression problems, but the thing is to do is just don't use any activation function at the end or output layer. Using linear activation function in neural network doesn't find any complex pattern, but simply acts as a linear regression problem. Okay. So we should be sure that this should not be linear activation function. Okay. There is a activation functions ReLU. Okay, rectified linear unit. So that linear is to be rectified. Okay. Then we can have a sigmoid. And a sigmoid is used only for binary classification. And even when compared to sigmoid, tan H is pretty good because of its steeply nature. So gradients are more non-zero. Okay. So in this slide, you can understand that activation functions are there. There is a ReLU, there is a sigmoid, and there is a tan H. All are popular activation. In a practical way, you need to. Linear functions are not used as activation functions. Okay. If linear functions are used hidden layers and sigmoid rather than we can simply say that hidden layers as useless. Because to bring complex features, we need a nonlinear function. Okay. And initialization of weights of neural networks. So, as we have seen, artificial neural networks, weights are important, activation functions are important, number of hidden layers are important, and number of neurons are also important. Epochs are important. So, activation functions are important. And the type of optimization we are going to bring, it is also important. There are many parameters which are to be, fixed. So, first and foremost, we need to initialize weights. By zero is not preferred. If you want to initialize weights by zero, this causes all the neurons or units in the layer to be same for every iteration in the gradient descent. So we initialize randomly, and we should be sure that initialization should be very, very small. If they are large than after applying activation functions on them. Okay. So gradient descent doesn't change the parameters much in sigmoid and tangent. In neural nets, hyperparameters, that is number of layers, hidden layer, and learning rates, these are the ones which control parameters. Okay. So you can understand that there is a need for everybody to find those hyperparameters. It is not a general one. It is going to vary from problem to problem. For each type of problem, we need to find them. Okay. We should explore and fix, and we should have a trade-off. Okay. If the data given is not large enough, then dividing it into train and cross validation test sets in the ratio of 60, 20, 20 is fine. But when there is a huge data, even 98 to 1 or 99.5.41 will be okay. So it is some sort of a pragmatic neural networks applications. Okay. If you are given a data, this is the ratio which you need to take. And there is a concept called dropout regularization. And all those things, whenever I worked on neural networks, I observed them. What we do is we take one training example and toss a coin and keep some nodes in the neural network and shut the others. And again, for the other examples, toss a coin, eliminate the nodes and do it for all the examples. So it is some sort of a randomization. Inverted dropout is one of the technique in implementing dropout. What happens there is, let us talk about a network and issues. We are on layer 3. What is step 1? D3 be a vector and D3 is equal to np.random.rand. Okay. And we made a D3 matrix which has same dimension as a 3 matrix or vector. And we are able to get key probability is 0.8. It means that 80% of the value should be there and 20% chance of eliminating units. So D3 is a matrix where 20% values are 0 and remaining are 1. In the step 2, we multiply A3 and D3, so 20% units become 0. Step 3, A3 is equal to, you are going to get a probability. Let there be 50 units in the third layer. Okay. So what happens? The dropout is to be implemented only on training set. It is not needed in applying for the test set. It applies. So it acts like a noise. What is the intuition of the dropout? It cannot rely on the one feature. So spread the weights. H of x is equal to W1x1 plus W2x2, so on W1, W2 are weights, which tends to or shrink the square norm of the weights. Okay. As in dropout, each time different units disappear, so the resultant unit doesn't exactly rely on one feature more, but instead it is vulnerable to all other equally, which leads to shrinking of weights. So as we have seen, if weights are very small, vanishing gradients, weights are very large, vanishing gradients. So you need to have some sort of a balance. So balance is achieved through normalization. What is normalization? We know about normalization in the vectors. Suppose we calculate the variance of the data and then perform x over variance. So all the features in x have same variance, that is data varies equally among all the features. Why we really require normalization? What is normalization? You can have data varies equally among all the features. Why we require normalization? The input, because when we call cost function, the contour will be like elliptical. So then gradient descent have to take more steps and oscillate to and fro to reach the minimum. Whereas when we normalize, we divide the data points by variance, which makes the distribution same for all the features. So the contour almost will be symmetric. It is not be, it will be circular. So naturally gradient descent, we can take larger steps and need not even oscillate and reach the minima quickly. So it will be easy to optimize the cost function when features are on similar scale. So neural networks people use nowadays, we are all using deep nets. When we initialize the weights slightly greater than 1, not 0, what happens is with the increasing number of layers, the activations increase exponentially in L, number of layers. So more the number of layers, higher the values of activations, which follows more the values of gradients, which makes large steps. Then similarly, if weights are slightly less than 1, then the activation values gets vanished and gradients gets lessened, which makes the steps in gradient descent very small and takes more time. So ideal situation is they should not be less than 1. If they are greater than 1, meaning of it is you should not take them very, very large. You should have a trade-off. What is the solution? When you are having greater than 1, one problem, less than 1, there is a problem. So how to handle this? One of the solutions is to initialize weights carefully when the activation functions. Used is ReLU, then the weights is initialized. Okay. This does not solve the problem entirely, but reduces it to a good extent. There is a mini batch gradient descent. Okay. You can take a small batch and apply gradient descent to that. And there is a moving average. Given a data set, a moving average of all previous points plus new point, number of points. So when the given data set is noisy, plotting moving averages decreases the noise and the line will become a bit smoother. Exponential weighted moving average or exponential weighted average. And there is a C209. All these are how we are going. There is a adaptive movement estimation. Okay, we some sort of optimization we do. Adam, batch normalization, covariant shift. How we can find the batch now? There is a softmax regression. In softmax, the output vector contains the probabilities, whereas the hardmax has 1 for the highest probability and 0 for the others. This is how you can have activation functions. So the greatest success comes from having the freedom to fail. It is by Zuckerberg. Okay. So in ANN we have supervised learning and unsupervised learning. So in the training data, what happens is the uses pairs of inputs and uses only input. There are no outputs in the unsupervised learning. Model learns to approximate the true solution based on the provided examples, whereas here the function satisfies the evolution across the entire domain without specific examples. Okay. So it is more challenging. Unsupervised learning is more challenging. There is a error metric. Error is calculated as the difference between the predicted solution and the known solution. Error is calculated based on how well the model's output satisfies the differential equation. Okay. Examples of use: predicting solutions at specific point when solutions are partially known, solving differential equations when the exact solution is unknown or only the equation is available. And complexity, less complex, it is more complex. Computational cost, lower, of course it is higher. And these tables are especially designed for differential equations. And in the supervised learning, we can have this unsupervised here. The activation functions we use are sigmoid, ReLU, TANH. Sigmoid and TANH are often used in the hidden layers of smaller networks. ReLU is popular for deeper networks due to its efficiency. And in the learning process, there is a training, forward propagation, and loss function. So this is the ReLU, leaky ReLU, TANH, binary step function, linear, SeLU, sigmoid, parametric ReLU. Okay. Suppose, let me show how to solve a differential equation. I'm taking a differential equation by using unsupervised method, and I'm taking 1000 epochs. Batch size is 100. 700 loss is this. 700 epochs loss is 0.08. 800 epochs loss is 0.09. 900 epochs loss is 0.07. Understand that increase of epochs is not going to decrease the loss. Okay. So whenever I do, this is the neural network approximation. This is the exact solution. It is almost near to that. It is a demonstrative example. Suppose if I do epochs of 10,000, batch size of 100, 9,700 epochs, loss is 0.0018. 9,800, loss is 0.0013. 9,900, 0.0014. You can see that 9,700 to 9,800 loss is decreased. But once you increase the 9,800 to 9,900, loss is increased. Okay. So we need to have a trade-off that you can understand. So similarly, I have taken another differential equation: d square u by dt square is equal to c square d square u by dx. Initial conditions are given. Okay. You can use finite difference method, neural network approximation. Okay. Whenever we do some comparison, here I am having batch epochs have gone up to 1,000, 700 epochs lost 0.39, 800 0.40, 900 you are able to get 0.38. Epochs is 100, batch size is 100. This is a finite difference solution. It's a neural network approximation. So if I increase epochs, you can understand that 9,700.32, 9,800.37, 9,900.36. You know that 9,700 is the trade-off. There you can stop. So these are some of the analytical solutions of this particular differential equation. If I use soft plus, this is the solution: ReLU, cos, sigmoid for different activation functions. If I take another differential equation, analytical solution is cos x plus e to the power of minus x, soft plus, ReLU, cos. You can understand that they are very much near. We worked on Lagno systems and able to, they are very important. We have run some simulations. You can understand that by using supervised learning, we are able to improve the accuracy. we worked on singular matrix differential systems. And here you can see that we are able to train them. And this time we are using what is called both supervised learning and unsupervised learning. Numerical solution versus numeral networks. You can see this is the architecture we have used. And you can understand that a loss is really coming down. Okay. Numerical versus neural network. You can see this. And if I take another example, and you can see here also we a training loss of RK23 versus neural network and relative errors of variables. And 0, 2000, 4000, 6000, 8000. We ran up to 10,000 epochs. Okay. And we have considered with stated specifications by training the ANN for 10,000 epochs. It clearly demonstrates that the network can capture the underlying structure of the singular matrix differential system with a precision of 10 to the power of -6. Higher precision can be achieved by increasing the number of neurons, number of hidden layers, number of epochs. Other activation functions or a combination of activation functions may further improve the accuracy. From the simulation, we observed that training with RK23 result in better accuracy when compared to that of RK45. So another problem is hyperparameter optimization in neural networks. Okay, so here we have done some heat map. Okay, there is a switch tends to perform better, especially at higher bits like 128 or 512. Final loss stay really low. Tan H starts off well, but with depth 8, it gets unstable. The loss jumps a lot in some cases. And here we are having another example where you can see activation show low losses across all configurations, but sigmoid becomes unstable at higher depths. ReLU and Swish maintain consistently low loss values, especially with moderate changing points. These are some of the experiments we have done. Okay, and we have done heat map analysis. And sigmoid often causes high or even exploding losses. And we are able to get some good results. And in this, I have not included, one of the things I'm especially doing artificial neural networks, we are using for cryptanalysis, and we are able to find distinguishers. Because it is a popular talk, I don't want to include my research in this, but just to demonstrate the importance of optimization. And just artificial intelligence, as it is told by us. So I would like to thank Dr. G. Sitaram Brahma, Mrs. G. Deepika, Mr. Sudeep Koktal, the research student at the University of Michigan, Jay Harikarthikeya, and Mr. Pudin, who is working with me. I would like to acknowledge them. And how is a final analysis history? All sciences are in abstract mathematics. All decisions we make have their rational in statistics. Is for efficient use depend on computers. It is told by Padma Vibhushan Professor Rao. Okay. Tasmai Sri. My thanks to my mentor, guide, teacher, Guru, Professor Narsimurthy Garu, under whose tutelage I am he is my guru. If you find any talk, you can. And if you find native, that is required. I would like to thank my guru. And thank you all for listening. I know how difficult it is. Uh,
Sir, thank you, sir. Thank you for the session enlightening, sir. We had very nice, you presented very nice presentation, sir. Here, all the online and offline participants required more knowledge. Whoever doing the research in the same area. So they are very much happy with your expertise lecture, sir. Thank you very much. Now I request all my dear online and offline participants, if anyone have the doubts, that means queries, please raise the hand in the chat box or unmute yourself and try to interact with our today's resource person.
Okay.
If anybody had queries.
Yeah, sir, am I audible? Am I audible, sir? No, I think from there your mic is connected now.
Hello.
Am I audible, sir? Hello, sir, my voice is reaching. Hello. I think network issue. Okay, then conclude.
Session. Sir, due to technical issues, actually we may not connect the line to the sir. So all the participants, don't worry, please post the queries in the chat box. We will collect all the queries and we will convey to the our resource person, Sundarananda sir. Later, or we will share the mail ID also. You can interact likewise also in further clarifications. Now, let me invite Dr. T. Ishwarlal sir, Associate Professor, Department of Mathematics, to share the session remarks on this today's session. Please welcome, sir.
Good morning.
Laptop.
Yes, speak.
Good morning, one and all, the participants online and offline. My name is Dr. T. Ishwarlal. Today, I am giving a briefing on the what lecturer, Sir Professor Venkata Sundaranand Pucha is a professor and HOD of Department of Mathematics, Rayalaseema University, Kurnool. Sir given a lecture on artificial intelligence and machine learning with optimization techniques and nucleus, which is explained briefly on neural networks and how the artificial intelligence is used and how to get a connection between these biotechnical and neural networks. Sir given an inspired speech on this and also very innovative. Those are doing the research and studying in PG higher studies in these areas. Okay, optimization with mathematical form and is given the differentiation to solve with stationary points and mathematical form with the optimization problems. And also local, global, explain locally minimum, locally maximum with contributions, people connected with with the methods of Newton's, Lagrange's, etc. And also George Byrne and Van Neumann's. What came to these are all this expertise for in the concepts of the artificial intelligence and neural networks. Further, Sir told the AI constitutes of with different models like speech recognition and how do human do it and how might computers do it. Is explained very nicely a process with big recognition of some more concepts which, which influencing and execution expert systems by knowledge base and the practical base. So this is one of the inspired lecture those who are worked in that area. Also, on overview experts, the classification of expert systems, applications, export systems with limitations. Further, explain a natural language processing, how it will works, and what are the fundamental aspects of human behavior which connected to these neural networks. Further, Sar went in differentiation model and also the graph theory, which explain the parsing trees which for uses of NLP learning system. That is natural language processing, and also he explained a soft computing, which help of fuzzy logic, neural networks, machine learning, etc. After that, Sar went for a discoveries, gold-based conjecture. That is a good solution is given for this conjecture with the mathematics that every even integer greater than 2 can be written as the sum of two primes. With a nice proof is explained, and that what we can understand from this discoveries from the mathematicians. Further, is connected the artificial neural networks with the all systems with brain and computers versus. With this lectures with also in machine learning in ANN models, artificial neural networks, and given a brief with functionary and functions with maximize and minimize and chromatic practical form and differential evolution, Hopfield nets and perception and machine learning, gradient descent algorithms. So many, this is a long run what we given this our lectures to explain all these things. We require so much time. So for the short, I'm briefing only. With this, I thanks to Sir to giving such a knowledge in the artificial intelligence and neural networks to understand in better way and doing and making interest in that areas. Thank you, sir, for your long speech and your presentation. Very much like, and we are follow this some of the instruction what you solved the problems further. Okay, thank you, sir. One and again, thank you, one and all.
Thank you, sir, for your comprehensive session remarks. Anyhow, let us continue the next session after a short break of. Actually, we missed one activity here. Actually, let us share one token of appreciation from our Department of Mathematics to the resource person. We are honoring you, sir. Please accept our token of appreciation.
Classroom. 11 to. Yeah.
PPT run. Slideshow. So please accept our honor, sir. So let us continue the next session after half an hour. After 30 minutes, we'll continue the session. By 11:30 sharp, again, we will join in the same link. I request all the offline participants, please have the cup of tea with snacks. All the necessary arrangements have been made in the room number F106. Please have it. And for online participants, please join in the same link after 30 minutes. We'll be again join in the
Thank you very much.